Hello, welcome to the Short Span Steel Bridge Alliance's 2020 topic-based video series. In this series, we'll review basic concepts and ideas pertinent not only to engineers new to short span steel bridge design, but those looking for a refresher of fundamental concepts. In this video, we'll discuss suggested fabrication details for short span steel bridges. The goals of this video will be to provide an overview of simple and economical fabrication practices for short span steel bridges, as well as to provide engineers with guidance on designing and detailing the steel girders for typical bridge projects. This video is part of a two-part series on suggested fabrication practices. The first part covered the overall framing system layout for a typical project. This video will cover preferred fabrication practices for individual girders and elements. An excellent resource on this topic is the AASHTO NSBA collaboration documents made freely available for engineers, specifically G12.1, the Guidelines to Design for Constructability. You can find this document at the link shown. You should note that this video only covers recommendations relevant to short span I-girder bridge options and those with spans up to 140 feet in length and those with relatively simple geometry. Keep in mind that it is always the responsibility of the engineer of record to ensure that all designs meet safety requirements as well as any applicable federal, state, or local standards. To begin our discussion, we'll look at limits on plate thicknesses. Certain minimum requirements for plate thicknesses are recommended to try and mitigate weld defects during the fabrication process, as well as to reduce deformation during welding. What this means for short span steel bridges is that when detailing stiffeners, connection plates, and webs, you should keep the thickness at a minimum of 1/2 an inch, which is usually not an issue for most short span bridges. For the flanges, the thickness should be kept at a minimum of 3/4 of an inch. Again, not an issue with most short span steel bridge design. In terms of plate widths, you should know that fabricators will cut plate components from standard mill plates. So when designing a given project, you should detail the flange widths and even the web depths so that they can be cut from as few standard mill plates as possible. For example, the most common plate sizes that are readily available are 72 inches wide or 96 inches wide. So you should keep that in mind when detailing components for a given project to try and reduce the overall amount of standard mill plates that need to be purchased for fabrication. By reducing the number of plates that need to be purchased, you'll not only improve the overall economy of the project, but you'll reduce waste as well. In terms of flange widths for plate girders, flange widths should be kept constant along the span. There'll be more on this later when discussing flange transitions. For the web depth can be influenced by a number of factors. For example, vertical clearance requirements, hydraulic opening requirements. Obviously, you'll want to detail a girder that's efficient and economical. There'll be a little bit more on this later. For plate girders, we obviously want to fabricate a girder that is as efficient and economical as possible. We have the option with plate girders to change the size of the flange along the span to improve the overall economy. To illustrate this, consider a simply supported plate girder. In simply supported situations, the high moment regions are near midspan and the low moment regions are near the support. To improve the economy of a given girder, a designer may choose to reduce the size of the flange near the support. This change in flange size is what we're calling a flange transition. You obviously have two options with a flange transition. You can either change the width or change the thickness, or both, I guess. If a transition is utilized, always maintain a constant flange width. Do not change the flange width in a flange transition. This results in much less handling of plate components on the part of the fabricator, and it results in a much faster fabrication process. Fabricators can weld standard mill plates together and then cut those plates out to generate the individual flanges for a given project. Whereas if the flange width is changed, each individual flange will need to be fabricated separately. This results in much more handling and ultimately a much more time-intensive and expensive process from a fabrication perspective. Now, one question's worth asking is, when should you incorporate a flange transition? A common rule of thumb is to only use a flange transition if it saves about 1,000 pounds of steel on your given project. Your state or local standards might have more specific guidance on this. I would urge you to reference those standards when making this decision. I would also make sure that you contact your local fabricator to get more guidance on the economy of a given design. Now, note on plate availability, you should always check with a local fabricator or a steel mill or the service center in your area to ensure that you have an adequate understanding on the maximum length of available plates. In this slide, we have a table that has been adapted from the previously mentioned G12.1. So for example, let's consider a plate that is 96 inches wide by a ½ inch thick. If you're wanting to procure a 96-inch wide by a ½ inch plate, that plate is pretty much going to be available at a maximum length of 81 feet. So for instance, if your project has a span length, for example, that is larger than 81 feet, you should always keep this idea in mind when designing and detailing the individual girder. Again, I would always check with your local suppliers to ensure that you have an adequate understanding of availability in your area. Here's some other miscellaneous guidance on fabrication details. First off, avoid the use of longitudinal stiffeners whenever possible. These are usually not necessary for short span bridges, and you shouldn't need to include them. In terms of transverse stiffeners for improving shear resistance, you should try and avoid those if possible. They're usually not necessary until the spans get over 100 feet long, and you definitely shouldn't need shear stiffeners for rolled beam solutions. Speaking of rolled beams, there really shouldn't be much of a need to field splice a rolled beam. Now, of course, this can change if you have transportation issues with your given site location and you need to bring the rolled sections in pieces. But barring those issues, you really shouldn't need to splice one. Applicable rolled sections for short span applications should be available in lengths up to 100 feet long, so it shouldn't be necessary to splice them. One final note on field splices: if you do utilize a field splice for your project, always ensure that the compression flange of each of the individual field pieces is at least L/85 wide. L/85 being the length of the field piece. This is a limit from the commentary of 610.3 of the AASHTO LRFD specifications to ensure adequate handling of the field piece during the construction process. There have been a lot of details presented in this video, and it may be difficult to understand where to start. Arguably, the best starting point for a given project is eSpan 140. By providing some very basic fundamental information within eSpan, such as the span length, the number of sidewalks, the speed limit, and etc., eSpan will provide a preliminary short span steel bridge design start to finish, including all necessary plate sizes and dimensions, all detailing requirements, etc. There are also solutions available for buried soil steel structures as well as prefabricated manufacturer solutions. eSpan is free and easy to use and can be found at the link shown, and it is a wonderful starting point to begin your design. With the recommendations that have been mentioned in this video, as well as recommendations in part 1, taking those recommendations as well as the output within eSpan and consulting your local fabricators, you should be able to produce a very efficient and economical design quite easily. That concludes this video on suggested fabrication details. We thank you for your attendance and look forward to you joining us in our next video. Thank you very much.